Hello stats class, here's lesson 5.3c, and it's actually just picking up where 5.3b left off with talking about when would we want to use that multiplication rule and when would we want to use a tree. When would a tree be best? And the example I'm going to do today, I'm going to do all three ways of organizing it just to show you, but first I'll talk about when would you want to use a tree. So the first thing is if there's more than two events. We've only done trees with two events so far, but if there's more than two, a tree is better in general. So let's think about what if there were three things happening in a row. If you tried to make a two-way table out of that, the reason it's called a two-way is there's only two events. So a three-way table would have to be three-dimensional, and I have seen stuff like that, but it's messy. You could theoretically do a Venn diagram with three bubbles. I don't think that it's possible with four bubbles, but three would be possible but messy, versus with a tree, you'd have your more than one branch here and then another thing happening after that and then another thing happening after that. And that's possible to do as many as you want, except that it gets messy after a while. Basically, anytime you have more than three events, it's really difficult to draw, but a tree would work well for that. The second thing is if there's a logical order to the events, one comes first, one comes second. So that could be time-wise, or it could be to the events. It could be that there actually is a cause and effect relationship, like the one we saw with the internet, where you can't have social media without having the internet first. So if there's a logical cause and effect relationship there, or if we suspect a cause and effect relationship, then it makes sense to make a tree because it's do this first and then the next thing and then the next thing. And then the biggest reason I personally would choose to use a tree is if the given information includes conditional probabilities. Because on a two-way table or a Venn diagram, there's nowhere to write those probabilities. And kind of like we saw that a two-way table gives you a place to write the totals, a tree gives you a place to write the conditional probabilities that go on these later branches. If these later branches are different, then a tree makes sense to do that. And that if you're not given that information, then any of the methods would work. But it's a really good reason to use a tree. So we're going to do one big example instead of a bunch of little ones. And I'm going to do a bunch of different things with it. And show you the tree and show you the table in the Venn diagram also. So let's talk about athletes. And studies show, yeah, they did a survey or something and they found that 2%, that's not very many, of Olympic athletes use steroids. And by the way, that's illegal and they would get disqualified if they were found out. They're not supposed to boost their athletic performance with steroids before doing the Olympics, right? But the test that tests them to see if they use steroids, I mean, the Olympic Committee, right, would test them and disqualify them if needed, but the test isn't perfect. In fact, that's true for all medical tests, by the way. There are some people who get a false negative, which means the test says they didn't use steroids, but they really did. So, and that's 5% of those who use steroids test negative in spite of it. Or there's also such a thing as a false positive. Sometimes somebody who didn't take steroids will test positive, and that's only 1% of those people. They don't use steroids, but they test positive anyway. And what's funny about that is, some employers do tests for illegal drugs and stuff like that. Poppy seeds contain opium in them. So if you've eaten a poppy seed muffin for breakfast, you're going to test positive for opium. And it's kind of funny to think about that. That happens to people, really. But it wouldn't mean that you were doing anything illegal. It's perfectly okay to eat those muffins, I promise. So anyway, this information we're going to organize, and then we're going to answer a question about it. And let's organize our information just a little bit. This 2% is just the probability of steroids. And I'm going to change it into a decimal. For me, personally, it helps to write this type of thing down. The symbols help me organize my thoughts. So that's what I'm doing. This false negative thing is 5% of those who use steroids. That's my given information, and then they test negative. So that would be the probability of testing negative given that they use steroids, and that's the 5%. And then we have the probability of testing positive without using steroids. And so you could call it probability of positive, or you could say NC for not negative. I think I'll use the SC since I don't know what I want to use for not steroids. I've already used an N for something, right? But regardless, as long as it helps you understand it, this is the 1%. Oops, I should have written it as a decimal like I did the others. Okay, so you could call this not negative. That would be true. All right, so we're going to take that given information and put it into a table, a Venn diagram, and a tree. And I'm going to start with the tree on purpose. The reason I'm starting with the tree is it gives me a place to write these two numbers. So we've got either, think about what comes first. Did they take steroids first, or did they test positive or negative first? I think they took the steroids first, or they didn't. And that is only 2%, or 0.02, and 98% down here. After they take the steroids or not, they test positive or they test negative. Positive, negative. And again, you could use the NC thing if you want to, or whatever. If you find yourself forgetting what these are, write them out. Write out the word steroids. Write out the word positive if you need it. So let's talk about where these go. The N given S, that's this branch right here. They took steroids, but they tested negative. That's the 5%. And this would be 95%. And then if they test positive, but they didn't take steroids, that's this branch, which is the 1%. And this branch is 99% of those who didn't take steroids test negative, which is correct. So let's label these with a little bit of vocab. This 5% I said was the false negative rate. This 1% is the false positive rate. These are very common things in medical tests of any sort. The other two have special names too, but you don't have to remember which is which. I'm just going to tell you because it's interesting that they have names. This one is called the sensitivity. And this one is called the specificity. But like I said, you don't need to know that vocab because you're more likely to see it given in a sentence or given in a symbolic form, which are the two things you really need to understand. So let's find the probabilities of all four branches like we were doing in 5.3b. This is 0.02 times 0.95. This is 0.02. I'm going to write them all out and then pick up my calculator. 5 equals, this is 0.98 times 0.01, and this is 0.98 times 0.99. You'll notice most of the population is in this group. Most of them don't take steroids and they test negative, and that's kind of comforting to know. If you multiply those together, that's 97% and a little bit more of all athletes. Most likely thing that would happen. These other three are much less likely. Taking steroids and then testing positive is a 0.019 or 1.9% chance. Taking steroids and testing negative is only 0.001, less, a tenth of a percent. And then this one comes out to be 0.0098, almost 1%. So those are much less likely than that one. And again, they would all add up to 100% if we were working on that. So now today we're going to do something different than what we did on 5.3b. We mostly were finding the totals and sometimes adding them together. In fact, let's do one where we're adding them together. If I want the probability of testing positive, that'd be this one and this one added together. Probability of positive tests is not very many people, actually. 0.019 plus 0.0098. I could do this in my head, right? 9 and 9 is 18, and that's 20288. So that's if you wanted the probability of being positive, right? Or if you wanted the probability of testing negative, you'd add these two, or you could do whatever combination you needed. I'm going to ask you an interesting question. What's the probability, if you find an athlete that tests positive, the probability that he or she actually took steroids? That's interesting because that's not the same as the positive given steroids. Positive given steroids, that's this one. Not that one. That's not what we're talking. Actually, it's this one. Probably a positive. Oh, I got myself mixed up. I'm sorry. So it's not the same as positive given steroids, which is this one. Not 90%. So let's calculate it because it's an interesting question. If I have a bunch of athletes and I pick one who tested positive, what's the chances they really had taken steroids? It's kind of a surprising answer, but what I want to do is I want to do the probability of both. This is using the definition of conditional probability divided by the probability of the given, which is the P, the one in the second spot. I remember it by, this kind of looks like a divided by sign, so it looks like we're dividing by P.